Hey, Physics 30s. Today we're going to start our next chapter called EMR wave theory. EMR, which is electromagnetic radiation, sometimes more commonly called light. Light encompasses the whole broad spectrum from radio waves down to X-rays and gamma rays, including visible light. So if I use the word visible light, I'm just talking about a very small section of light. But we also scientists like to call light EMR. This chapter and the next chapter encompasses the whole idea of what EMR is and how it can behave differently depending on the different types of experiments. This whole chapter is about how it behaves as a wave. Like all the stuff we talked about in Physics 20, where it reflects, like waves reflect, where they refract, where they change speed based on what medium it's going through. So we talk how light can behave very similarly as those. And then the next chapter, we're going to be talking about how light behaves as a particle. So we'll think about Einstein and Maxwell Planck, or not Maxwell Planck, so just Planck, how they discovered the photon, how solar cells, like solar panels, how they actually work, and how light can explain some of that. It gets a little bit more complex, but we'll talk about some of the experiments there, and we'll also be talking about if EMR can behave as a wave in a particle, so why can't particles, such things that have mass, behave as if they're waves? So when we get to the end of that chapter, we're going to be talking about de Broglie. So I'm listing all these names off. We're going to go through these names. These are just names you have to know. We'll talk about de Broglie, where he said that electrons can behave as waves in different situations, and they behave in particles as different situations. And we just call that the wave-particle duality of matter. So this chapter, we're just going to be talking about the wave theory, how light behaves as waves. Okay, so what I was talking about before is that we know that electromagnetic radiation, shorthand is just EMR, sometimes commonly called light, as I said. So if I'd say what spectrum of light is, I'm not talking about color of light, that's visible light. I could be talking about radio waves, I could be talking about ultraviolet, I could be talking about infrared, X-rays, gamma rays, cosmic rays. I could be talking about all different types of rays. You can see that later on. And I'll talk about what you have to know, what you have to memorize based on the wavelengths and the frequencies of those. Okay, so we're going to recall a specific scientist from the last chapter, and the scientist Faraday. We'll also recall another scientist, also just called Ørsted. If you remember those two scientists, Ørsted said that a current carrying wire or a moving charge produces a magnetic field. And Faraday says that if I move the wire through a magnetic field, I can produce current. So there's this kind of symmetry in nature. So that's what this is saying, discovered here. But he also thought that because electricity and magnetism are the same, because I can produce one using the other. So I can use electricity to produce magnetism, I can use magnetism to produce electricity. So that's what Faraday was saying. So I got like the generator effect and the motor effect. He was also thinking that light could also be affected by a magnetic field, and that essentially it might be the same thing. And he was pretty encouraged. He had an experiment. It's called the Faraday effect. It's not the link that I show here. This link down here it's kind of a garbage link. You probably should get rid of it. I'll put a link in the classroom that leads you to a better experiment, maybe 2 links there. It talks about the Faraday effect and how magnetic fields can affect the polarization of light. Now, we'll get to what polarization means at the very last thing of this chapter. It's essentially just how your sunglasses work. It's how it filters out light that are going in certain directions. And if I can turn the light using magnetic fields, I can see that the polarization has changed. And if magnetic fields can change the polarization, that means the light that it's changing the polarization of must also have something to do with magnetic fields, because magnetic fields interact with other magnetic fields. So he was very encouraged that when he saw this light passing through a heavy glass and it was affected by a magnetic field, that it actually worked. But the problem is that Faraday had all these ideas, he had all these theories, but he couldn't prove it. He didn't have the math skills to prove it he showed him maybe an experiment, showed this, observed this experiment, but he had no idea why it was happening. So another scientist came along, James Maxwell. So James Maxwell is one of the first famous scientists in this chapter, and he had a lot of theories and a lot of ideas, but he came up with five predictions of light. And again, he was very good at math. He took all this idea, ran with it. He developed this whole theory of electromagnetic radiation. It's very math heavy. We're not going to be talking about too much about the math. We're just going to be talking about the predictions of his theory. So let's go into the predictions. It's based on Oersted and Faraday, where Oersted said electric current produces a magnetic field, and Faraday said that a magnetic field produces current, and they go back and forth and back and forth. Now, what Maxwell proved mathematically, he proved that, well, I'll just highlight these guys because why not? Right? He proved that changing one of the fields, so changing a magnetic field or changing an electric field, produces a different type of, produces a changing field in the other one. So if I say, you can see here, his first prediction, his first idea was that if I change the electric field, because usually the electric field is just constant. So you have an electron just kind of sitting there, just producing a nice constant field around it. But if I were able to change it, then you can also produce what we call produce a changing magnetic field. So that's what this is saying down here. You really don't have to know what this equation does. It's just saying that if I change, remember that delta stands for, if I change the electric field here, there should be a little thing on top of that, over time, then I can produce a magnetic field. Okay, that was his first thing. He said it was also proportional as well. So if I were to increase my electric field, I would increase my magnetic field. Okay, so they're directly proportional to each other. If one was 0, the other would also be 0. That's very important when we talk about this diagram. We're going to be doing like an up and down motion for one field and a side to side motion for another field. It's one of his predictions that they end up being perpendicular to each other. Now, he kept on going on. He said, so I can produce this magnetic field by changing the electric field. And that's what Oersted said. If I move my charge, so my field is now changing, I produce this like nice little concentric circle magnetic field. Then he said, okay, now what if I change this magnetic field? If I change the magnetic field, can't seem to highlight, there you go. If I change the magnetic field, I can change my electric field. So my magnetic field changes, my electric field also changes. I should probably put those little vector arrows on top of those things. If my magnetic field goes up, then my electric field goes up. And this is just essentially what they're saying about the generator effect. If I move the electric or magnetic field or wire in a magnetic field, the magnetic field is changing around that wire, and the electric field changes, and a current is produced. Okay, so now what this is all fine. I think these are exactly what Oersted and Faraday said, but he went a little bit further. Now he said that what if I accelerate the magnetic field, accelerate this charge? So the field is always changing. Okay, so if I go back here to this one, so rather than just being a constant change, what if it's always changing size? Because if it's just a constant change, it just produces a constant field. But now if I increase the change, if I accelerate the movement of maybe the charge, my magnetic field gets a bit changes. So as it goes faster and faster and faster, the magnetic field goes up. Sorry, I'll try my hand this way. So as I go faster and faster and faster, the magnetic field starts going up. That's producing this changing magnetic field. So if I were to accelerate this, if I were to keep on changing the change, so I accelerate that, then this would also change. So you can kind of think of that as like I'm going to change the change, right? The change of the change of. By doing that, you just change the magnetic field, okay? But then you change the magnetic field. If I go down here, if I change the magnetic field, I produce an electric field. And if I produce an electric field that's changing, then I produce a magnetic field. If I produce a magnetic field that's changing, then I produce an electric field, and it goes back and forth, back and forth, back and forth. And by doing so, one field produces another field, the other field produces the other field, and then it starts propagating outwards. It starts radiating outwards. That's what the radiation part of electromagnetic radiation is all about. It's radiating outwards. Now, this radiation is not like the dangerous type of radiation. Sure, like X-rays, gamma rays, they are dangerous because they ionize. That's what they call ionizing radiation. We'll talk about that in the last chapter. But these ones are just propagating outwards from the source. The field is making itself as it goes. It'll start losing energy as it propagates through certain sources. Like light doesn't go on forever through certain mediums. Even in a vacuum, it'll go on for a very long time. Like we can see distant stars. But through like water and stuff, it'll be absorbed by the water, the energy. Eventually the waves will start decreasing in size. So that's what Oersted said. If I can get the field to change its change, so one way to do that is to accelerate a charge, then I can produce a change in magnetic field. And if I produce a change in magnetic field, I can produce a changing electric field, and et cetera, and going back and forth, back and forth. So that was his first prediction, right? His first prediction about electromagnetic fields is that you can produce them by accelerating a charge. Okay, so my charge is not moving at a constant velocity. If it's moving at a constant velocity, all it's doing is just producing a magnetic field, a nice constant magnetic field. I had to accelerate it to produce the EMR. So EMR is being produced all the time through wires. I have electric cords all around me. The wires in our house, power lines, radio waves in our phones, right? These are being produced because what's happening here is I'm just accelerating electrons in my radio antenna or my microwave antenna. So as I accelerate them, so all they're doing is just jiggling back and forth. But when they jiggle back and forth, they accelerate because they got to slow down, then speed up, and then slow down, then speed up, and then slow down, then back and forth, back and forth, back and forth, continually accelerating. As it continually accelerates, depending on the speed of the electron, depends on what kind of electromagnetic radiation we produce. So like these, we produce a kind of a broad spectrum microwave, radio wave towers produce obviously radio waves, lasers can produce laser light, visible light, and stuff like that. So all you're doing is just accelerating a charge back and forth. Now, these are all predictions. Most of these predictions he wasn't able to prove. He was able to prove them mathematically, but it wasn't until some other scientists came along to help him. So one of his other predictions was that the frequency of the oscillating charge, so think about this charge that's going up and down, that's being produced in your phone, is the same as the EMR wave that's being produced. It's the same as the EMR wave, right? There's a lot of highlight in this one. Let's just highlight it all, okay? So the frequency of the charge is the same as the EMR, and this was proved by Hendrik Hertz, what the namesake of frequency is from, like where you get 5 hertz from is from Hendrik Hertz, and he proved this using an experiment. There's a little video down later on. We'll talk about him within this lesson, actually. He also said, okay, if light is EMR, okay, that means all EMR, radio waves, all the X waves, must travel at the speed of light. And they obey the universal wave formula. So this is from Physics 20. Remember the universal wave formula said that the speed of a wave is essentially just its frequency times its wavelength. Okay? So since the speed of the wave is the speed of light, now the speed of light is denoted by the letter C. People say it's called celestia, some Greek stuff about stars and lights and stuff. But C is the speed of light, which is 3.00 times 10 to the 8 meters per second. So I could just say that if we're talking about EMR, rather than using a V here, I can just say C is equal to F times lambda. Because if it acts as a wave, it must have a frequency, it must have a wavelength, because that's what waves have. Oscillating electromagnetic fields. What that's about. Oscillating electromagnetic fields. are always going to be perpendicular to each other. Now, this one's a bit harder to prove. We can prove it by using polarization. That's much later on. We can block out one of the fields and then measure one field and then block out the other and measure the others. And then notice that they're perpendicular. So you got to think about this as kind of a little dance. If my electric field is going up, then my magnetic field is going side to side. Now, the thing is, they both start here, like the middle of my picture here is 0, 0. One is going up. The other also goes up out to the outside. So the proportional. So if one goes up, the other goes up. Then they come back and they meet down the middle. And then one's going to go down and it's going to go over. And then it's going to come back to the middle. And then it's going to continue doing that. Okay? So one's going to go up and they're going to be 90 degrees to each other. And they're perpendicular to the propagation of the wave. So I'm doing this. One's going up and down. One's going side to side. I'll just have to do this way. Right? Doing this up and down, side to side. But they're also moving this direction. So they're going this way. That's the movement. One's going up and up. One's going side to side. So up and down. One's going side to side. And that's propagation. So everything is 90 degrees to each other. Kind of just like the hand rules that we had from the previous chapter. So they're all perpendicular. It's hard to see this. Sometimes it's hard to draw this. Maybe I'll show you a picture in the next couple lessons here. Then also consider transverse waves. Now, transverse waves, we talked about physics 20. There are two types of waves, transverse waves and longitudinal waves. A longitudinal wave is something that's like in a slink. It's a compression wave. My voice is a longitudinal wave. It compresses the air in front of it, and that pushes the air up here and compress. It's just like a compression wave that's moving through the medium. The most sound is that way. But there are transverse waves. So you can get a slinky to go up and down, like a string in a guitar, where it kind of vibrates up and down. So that's what a transverse wave is. A transverse wave is one of these up and down kind of waves, right? So if the motion of the wave is this way, the medium actually goes up and down while the motion of the wave goes this way. Remember, it's waves. The energy is transmitted. The wave is moving this direction, but the energy is kind of going up and down. The medium is going up and down. The energy is transmitted sideways. So the medium goes up and up, down, transmitted sideways. But the thing is, waves don't need, light doesn't need a medium. It travels through vacuum because it propagates its own wave. So as it's changing one electric field, it's changing the magnetic field, and then it propagates itself. So it doesn't need a medium, but it has the same kind of idea of this transverse waves. Now, transverse waves have a bunch of properties we're going to have to talk about. And I think there's 5 properties of a transverse wave we talk about. In physics 20, we talked about a few of them. Transverse waves, all waves actually, reflect, okay? All waves also refract. And they diffract, okay? Refract, diffract, or diffract. They polarize. I'm putting this kind of in the order that we're actually going to be talking about. Now, diffraction, we'll talk about diffraction later on if you don't understand what that is. These are just the properties of transverse waves. And the last one is they interfere. Okay. So most of these, like the top, at least I think we talked about the top 4 in physics 20. Reflection is things where it kind of bounces off a wall and comes back. Refraction is where it goes through the wall, through the medium to the other side. So that's why certain classes you can hear the walls, right? Diffraction is where it kind of bends around objects. So you don't need a direct line of sight to hear me, right? You could be in a hallway or something and you'd be able to hear me still. Interference is like the law of superposition. When you have 2 waves and they're the crest of the waves, when they come on top of each other, they add up. If you have a trough and a crest, when they come past each other, they will cancel each other out for a bit and then pass through each other, but the law of superposition. I'm actually going to put that right there. That's not explosive superposition. Superposition. Okay. Where waves start adding to each other. We didn't talk about polarization because we didn't have this idea that Waves could be going in all different directions. They don't have to be going side, side, up, down. They be going off at angles, but they still have to be 90 degrees, the two waves, the electric field and the magnetic field. So they're going at this direction. They could be going this direction. They could be going off at any one of these directions. So polarization means I can try to filter that out. So maybe I just want this away. So I'm trying to cancel out the other one. So that's what your sunglasses try to do. They try to cancel out waves that are going in different orientations than the ones you want. Okay. So what I'm going to do, so what I'm going to do is I'm just going to stop here. I'm going to have two parts to this video. There's a lot to ingest at this point. And I'll see you in the next video. Bye.